2 missions lost. Okay, Mars Global Surveyor was working, but 2 fundamentally important lost. Well, what we did was this. We flew a pair of robotic geologists led by a great scientist like Steve Squires and his team, many 50-odd women and men, to explore Mars chemically at the scale in which geologists work. And you might say, well, that sounds scary. Geologists look dirty. And in fact, they work in the dirt to read the records of planets. And I like to tell the story. Here's the rover Opportunity poised about a year ago at the rim of the Victoria crater. I like to tell a story because when I talk to children about Mars and the universe, I like to remind them that I have never met a rock that lied to me, ever. As a scientist, we can read the record in these rocks, in these records, and understand, for Mars, the history of water, and thus the potential history of habitats. And by looking at the history of these rocks, perhaps reflecting an era 2 to 3 billion years ago on a planet that may have been hospitable, one that we'd like to have been, and we believe could have been, we start to gain insight into our own history. Before the Mars meteorite discoveries and announcements by Dave McKay about 13 years ago, we didn't think to look for nanoscale records of life in our Proterozoic here on Earth. We did not think to. Ask Jerry Soffen. I'm not making this up. We thought pretty much, well, the big explosion occurred, the atmosphere evolved, and our planet became the clement place that led to all these things. Well, we learned by looking at Mars and its rocks, so the meteorites, that may not be the way we should think about things. And these paradigm shifts are what have punctuated the history of Mars exploration. You all know we went from the Viking era to the modern Mars exploration era that we have through the rovers. Now, one of the things I'm most proud of about the Mars program, and perhaps it's not played well in the press, is the Mars Reconnaissance Orbiter, or MRO. We put this mission in place, in particular, to give us the kind of reconnaissance to plan the future. Tactical reconnaissance and strategic reconnaissance are important in science. We do it for the universe, through Hubble, through Chandra and Compton and all the great satellites that we have. We also need to do it for planets. And the scale we had seen Mars at from Viking was this background. The scale we saw from the Global Surveyor, here's a crater in the southern uplands, was this scale. The scale we saw from Mars Odyssey was this scale. And we realized that wasn't enough. We needed the chemical scale and the topology scale, the morphology scale, as if we were there. That will guide our planning of where we can go. And we presented the idea of this mission in 2001 to the President's Office of Management Budget. And we said, you know, there are thousands of places we'd want to go, with people, with machines, however. But we can afford to go to a few. So when you're planning your summer vacation on Mars, which one can you afford to go to? I'm not being facetious. And we've used these records. Here's a patch of ice near the polar layered terrain in the north, the NPLD. Nice little thing. Looks like a horse, but it's actually a few hundred meters across. One of the early images from the Mars Reconnaissance Orbiter. This mission, here's the sand dunes and layers in Candor Chasma. This mission has produced now 35 terabits of data. That is more data than every single other mission of planetary exploration in the history of NASA. One mission. It's in its first extended mission now. And this kind of capability is really important as we make the decision to go to the next step on Mars, or wherever. One of the things we did was fly a cooperative experiment with Italy that allows us to use long wavelength radar to see into the layers and sediments of Mars and into the ice cap. This is the North Polar ice cap with the spiral canyons. Here you see the record through sounding radar, the Charade experiment as published in Science by Roger Phillips. And what we've seen now is the grounding line of the ice, layers that reflect the climatology of the planet over millions of years, not billions, millions, the way it loads, in fact, the upper crust, the northern crust of Mars, and whether there are lenses of potentially frozen layers that may have reflected different climate states. We've also used imaging and radar to see the record of buried ice, not only at the poles on Mars, but in areas near the equator. And these are stupendous findings that may have been glimmers in the eyes of the former era, but now are quantified. Today, the record of Mars is quantified. It is a water planet. There's no getting around that. How much water? We'll continue to debate. That's the fun of science. There may be literally frozen ice sheets the size of Antarctica around Mars. We don't fully know that yet. That's one of the things left to discover. But the Mars Reconnaissance Orbiter has given us the ability now, finally, to see into those records in 3D. And the next steps will be even bolder. So MRO continues to do its spectacular work. I've just shown you that. The other thing MRO has allowed us to do is zoom in. Sorry about that, I went a little too fast. Zoom into the kind of places we want to go to. Where can we afford to send the flagship missions to Mars that will ask the tough questions? Where are the building blocks of life ever there? So the first mission in that sequence was the first fully completed mission to Mars, the Mars Phoenix lander, built out of the legacy of the Mars 01 lander that we did not fly, wisely, recompeted with new instruments, a new science team, Peter Smith's mission with many colleagues at University of Arizona. It launched a couple years ago as the first competitively selected Mars mission in history. I like to tell our great colleagues out there, this was like science does the Olympics. We had a competition, and of the 20 finalists, we down selected to 4. They were the gold, bronze, silver, and alabaster medal winners. And then we selected the gold medal winner, and they went to Mars. And they landed with a pulse descent motor system, a new way of doing entry, descent, and landing. And they operated for 153 days in the northern polar regime, an interesting area of climate on Mars. They surveyed the landscape, and they provided measurements, some of which had never been seen before. One of the things that was most exciting was the way in which our Mars program came together. Here's an image of Phoenix landing from Mars Reconnaissance Orbiter. This is like finding a needle in a haystack, folks, pointing a large camera the size of an astronomical telescope at a vehicle screaming in at hundreds of meters a second. A real statement to the team. The engineering that enables the science you see here has been the story of Mars exploration. Of course, we like to see the sunset over the polar climate of Mars. We watched the wind. We measured the boundary layer. These are seeming esoteric aspects of understanding Mars. We did, in fact, spectroscopically detect the HOH molecule, water, confirming the Odyssey results that there is a water table, an ice table on Mars. You can see the digging down to tens of centimeters. This is the blast zone under the lander that exposed ice. We're now convinced, in fact, as the polar fall set in, that these white deposits are water ice mixed with CO2. So Phoenix, in 153 days, confirmed our observations and presented new ones to us that told us how tricky it's going to be to really ask questions about life as we understand it on Earth on another world. Of course, there's the Wally moment for Phoenix last November. So what's coming? Well, a lot of people have talked, literally, about the mission that I'm now going to talk about. And I'm very proud of the mission. It's called the Mars Science Lab. The rover on the Mars Science Lab here, some 850 kilograms of flight system, has been named Curiosity by a young woman in a competition, I think run by Disney. But this mission was put in place in 2001 as the first bold step back into asking whether the chemical building blocks of life could exist on Mars in the right conditions. You might say, well, didn't we know that? Isn't that obvious? Or is it absolutely heretical to think? Well, it was heretical after Viking to think that we would go this far. So this particular vehicle, now nearing launch date in November of 2011, after the launch slip, is the most powerful scientific observatory on a planetary surface ever imagined. I ask you to refer to our great Apollo astronauts, because when I first described this to Gene Cernan, the last man on the moon, he said, wow, you can actually do that? Maybe thinking that it might not be as easy for us human geologists to do what this particular spectroscopic mass spectrometer laboratory can do. But this is the step I would maintain with all of you, to give us the confidence to consider those bold voyages of some future time with humans to Mars, things that I think are important. So what is MSL? MSL is a roving field laboratory, not a geologist, but the kind of roving field lab that will land on a helicopter-like jet-powered rocket system that we call the Sky Crane to prevent contamination of the site. We'll actually winch down the rover. It's 3 times the size of the Mars exploration rovers, about the size of a Mini Cooper. It's powered by this wonderful backpack here. Notice no solar panels and no hydrocarbon fuels. It's powered by several tens of ammonium. That will allow it to operate and do the kind of measurements you see here. This is a remote elemental analyzer known as ChemCam, one of the experiments designed with cooperation of French and Los Alamos. We have a drilling system, a sample handling system, and an experiment payload known as SAM. Not sure why SAM wasn't Sue, but we call it SAM. SAM is built right here in Maryland. undergoing testing now. SAM will process